In this experiment, my partner Colin and I had to design and race a mousetrap car. Our goal for this experiment was to understand Newton's complex laws a little better. Before we started to build the car, we learned a little about Isaac Newton. Newton was a well-known mathematician, astronomer, and physicist. He was very famous for his discoveries on motion. He created 3 laws of motion, which we will explain in more detail later. These discoveries, along with many others, helped advance science to where it is today. After learning about Newton, we started to make the car. Step 1 was to prepare the mousetrap. To do this, we used pliers and glue to make a spring arm. Step 2 was to make the frame. To do this, we glued 2 side rails to the bottom of the mousetrap. The next thing we did was mount the axles and the wheels to the frame. The last step was to attach a string from the snapper arm to the front axle. This car works by rolling up the string at the front axle and then letting go. When you let go, the arm flings backwards, pulling the string and rotating the wheels.
Newton's first law of motion is also referred to as inertia. It states that an object at rest stays at rest, and an object in motion stays in motion with a constant speed unless acted on by an unbalanced force. Here, the car starts off as being at rest until the force from the lever arm expels the car forward. The lever arm, along with the winding up of the string, act as the outside force which sets the car in motion. On the other hand, the car is currently in motion but immediately gets stopped by the wall. The wall is the outside force that stops the car from staying in motion. Finally, the car is in motion but gradually starts to slow down until it comes to a complete stop. Although it may not be as obvious as the wall, there is still an outside force acting on the car. It is friction. Friction occurs when one surface of an object rubs against the surface of another. In this case, the wheels of the car were rubbing against the floor. Without the friction acting on the car, it would be able to travel at that constant speed forever until another force stopped it.
Newton's second law states that the acceleration of an object is dependent on 2 things: the force acting upon an object and the mass of an object. There are 3 different ways to write this equation. The first way this equation can be used is force is equal to mass times acceleration, or force is equal to ma. We used this equation when we wanted to find the force of the car. To find the force, all we did was find the mass and the acceleration and then multiply them. The second way this equation could be used is acceleration is equal to force divided by mass, or A is equal to F over M. Using this equation is how we modified our car. To get more acceleration, we would try to get more force and less mass. The final way this equation can be used is mass is equal to force divided by acceleration, or M is equal to F over A. Since we could just weigh the car, we didn't use this form in the equation. This is a good equation to know though, just in case you are doing a calculation and don't know the mass.
Newton's third law of motion says that for every action, there is an equal and opposite reaction. If one object exerted a force on another, the second object would apply the same amount of force back onto the first. As the car hits the wall, it exerts a certain amount of force. In order for the car to come to a complete stop, the wall has to push back on the car with the same amount of force the car originally put on it. The weight of the car also applies to Newton's third law. The weight of the car pushes down towards the surface it is on, while the surface pushes back up onto the car. In this picture, the weight of the car pushes down on the table. The force from the table pushed back up onto the car with the same amount of force. Finally, the friction from the wheels of the car to the floor also align with Newton's third law of motion. As the wheels try to spin on the ground exerting a force, the ground puts a force on the wheels in the opposite direction. This allows the car to move along the ground. The amount of force applied from the wheels of the car is the same as the friction from the floor. Eventually, the car will stop moving and become at rest due to friction.
Our goal of this experiment was to learn about Newton's complex laws. Although this experiment did not completely teach us his laws, it helped us to understand them a little better. The car helped to explain Newton's first law because when it was in motion, it didn't stop unless friction or an outside force acted on it, and when it was at rest, it wouldn't move until the force of the snapper arm caused it to go. This car helped us to understand Newton's second law better because we had to use his second law to modify the car. We figured out that more force and less mass would make the car move faster. This car also helped us understand Newton's third law better because we could see how action and reaction forces worked on a real-life model. All around, this experiment helps us to have a hands-on demonstration of what we learned about Newton's laws.